Thibaut Richert. So Thibaut is energy system engineer, data scientist. His background is actually civil engineering, sustainable energies, fluid mechanics, and thermodynamics. So very nice diversity. He spent time researching how traditional siloed energy systems are evolving towards complex cyber-physical systems with a high degree of cross-sectoral integration. He actually just finished his PhD in December from DTU, and he's working now, it will be presented, sorry, the topic was modeling operation control of power to heat units in integrated energy systems. And specifically, today is presenting about simulating services from cross-domain components in integrated energy systems. Lucas, it's all yours, and it would be great if you could try to make it in 15 minutes. Thank you.
Yes. Hello, can you hear me?
Yeah, very well, Thibaut. Yeah. Can you share your screen? Yeah, great.
Is that working now?
It does. Thank you.
All right. I'll just put a timer and get started. Yeah. Hello, everyone. So I'm Thibaut Richert, and today I'll present you some work I carried with Jensen on simulating services from power to heat components in integrated energy systems. So I'll give you a bit of introduction and background, and then walk you through the methodology, apply then to a case study, and before discussing some results and giving some final key messages and open questions. So the context of this work is actually based on the EU energy transition strategic energy technology plan, which calls for a better integration of energy systems in the future years. More specifically, a strong coupling between the electricity and the heat sector, and these two primarily support the operation of the power system and at a higher level facilitate a cost-effective transition towards a carbon-neutral and resilient energy system. And this is to be achieved by using the flexibility potential that exists in district heating systems. So traditional power systems have been very centralized, vertically integrated, very few actors, and as we all know, they are evolving to complex structures. So in Denmark, in the context of this study, for instance, we have a strong penetration of wind power in the power system, large-scale PV, many actors coming into play, like several DSOs, and also proliferation of distributed energy resources that are also calling for new actors such as aggregators. On the other hand, we have district heating systems which have been traditionally operated with a central heat source that is delivering heat to end consumers via a network of distribution pipes carrying hot water to substation where the heat is exchanged to the consumers. And these systems have evolved through several generations of district heating systems. So from the first generation based on steam with very high operating temperatures above 200 degrees, to the second generation where pressurized hot water systems came into play, which drastically decreased the temperatures. Still, the energy mix was very singular with only CHPs. And now Denmark is at a well-established third generation with temperature levels below 100 degrees, a fairly diversified energy mix with large-scale solar coming into play and like CHP, biomass. And there is a strong evolution towards the so-called fourth generation.
Thibaut, sorry to interrupt you. Can you speak a little bit louder? Apparently, you're not being heard very well. If you could just speak a bit louder, would be great. Thank you.
Is it better now?
Much better. Thank you.
Okay, sorry. Yeah, so the fourth generation, these systems are evolving towards the so-called fourth generation district heating networks, where the energy mix is actually much more diversified and mainly through heat recovery from data centers or industrial processes, a strong focus on multi-timescale storage from seasonal to weekly to daily, and a strong coupling to the electrical grid with centralized heat pumps and decentralized heat pumps. So physically speaking, integrated energy systems looks like this, and in this paper we actually focus on electrical and heat systems only, where both infrastructures actually deliver energy to the loads, and we have coupling technologies such as power to heat units that convert electricity into heat. So taken together, these systems actually undergone individual digitalization. So in the electrical system here, we see the well-known smart grid concept, and the equivalent of this heavy digitalization would be the 4GDH in the district heating. And taken together with the physical coupling, they actually represent the integrated energy system that we are focusing on talking about today. And what is special about these is that electrical systems are fast, so they have operational timescales in the order of seconds or below, and they are very geographically spread from transnational to national to very localized systems, and their control is usually complex with several layers and entities involved. On the other hand, district heating systems are very different, so it's hot water flowing into pipes, so these systems are slow moving, with the operational timescale in the order of minutes to hours. They are localized, so there is no such thing as a transnational district heating network. And their control is fairly simple with few entities involved and few layers of control. So current practices in modeling these integrated energy systems are either focusing on a very detailed unit model that are highly complex and usually abstract to a very high degree the rest of the system in which the unit model is deployed, or very high-level abstracted models such as Balmoral or Energy Plan, which are low to medium complex and also abstract part of the system and oversimplify some of the system. So with this paper, we actually tried to develop a complete tool chain for simulating integrated energy systems, and more specifically the dynamic operation of power-to-heat units in such context. We also tried to look at characterizing the effect of neglecting dynamic modeling of the thermal delays in district heating networks, and finally looked into the trade-off between computation time and simulation outcome accuracy within the dynamic simulation of district heating network. So to do so, we followed a use case-based or use case-driven approach to simulate like power-to-heat units providing downregulation services to electrical DSOs. So we chose such an approach to narrow down the scope of our simulations and better identify the necessary functionalities and requirements of the simulation tools. And here on the right, we can see an abstracted representation of such a system where we have a power-to-heat unit which is physically coupling the district heating, the distribution grid on the electric side, distribution grid on the district heating network side, together with their respective control entities on top of it, namely the DSOs. So to do that, we actually developed a co-simulation toolchain using MOSAIK, which is a flexible smart grid co-simulation framework, which basically allows you to create an entire ecosystem of several simulators that are addressing a common problem and communicating and orchestrated together through MOSAIK. So to do that, we've built a power system simulator in Python using PandaPower. The control domain has been modeled explicitly in Python as well as the cross-domain units, so namely the power-to-heat units. District heating network model was programmed in Modelica, more specifically in the Dymola modeling environment, and interfaced with MOSAIK through the functional mockup interface. So basically, the district heating network model was packed together with its solver into an FMU, which is a functional mockup unit. And we have built a district heating interface wrapper around the FMI++ library in Python, which is basically a facilitator to interact with FMUs at simulation runtime in order to interface it with the MOSAIK scenario. The power-to-heat unit considered here is a heat pump, a single-stage vapor compression heat pump that has been custom-tuned to include some thermal constraints arising from the integration of the heat pump into a thermal system. And these constraints are to bound the work that can be provided by the compressor of the heat pump. So there is a constraint with the lower temperature limit at the cold side, the evaporator, because you don't want to freeze the water that you're cooling down, and an upper temperature limit on the hot side, namely the condenser, because you don't want to start boiling the water that you're heating up. And the work that the heat pump can then provide is bound by these thermal limits, as well as the rated work of the compressor. So our use case has been applied to an existing case study using our co-simulation toolchain in NORDHAVN. It's a district in Copenhagen, Denmark. This area features both an electrical and district heating network, and we've performed low temperature district heating simulations with supply around 65 degrees, return 35 degrees, using the real topological and time series data that have been provided by the respective local DSOs for simulation horizon of 24 hours. So here you can see the network topology. On the left, the district heating network with the heat source on the top left corner, and then the network of pipes serving the different consumers marked by the square boxes. And down here we have deployed a heat pump in a return supply manner, meaning that the cold side, so the evaporator, was deployed in line into the return line of the district heating, and the condenser, the hot side, was deployed in line in the forward line of the district heating network. So when operating, the heat pump is actually cooling down the return water to heat up the forward line in the district heating. And together has been deployed a photovoltaic installation. And on the right here, you can see that there is the equivalent of the electrical network, and both units have been deployed in the same feeder to actually see how the heat pump can be used to do some peak shaving of excess power of the PV. So the outline of the control system deployed here is as follows. So each of the gray boxes represents a simulator that has been plugged into MOSAIK. So we have a power to heat unit, district heating network, the electrical grid, and an explicit modeling of all the control architecture with an electrical DSO, an aggregator, and the local power to heat controller. Several simulation scenarios have been considered. So a base case with no heat pump using all the real heat demand signal, and same for the electrical side. A step activation of the heat pump to isolate its effect using some flat heat demands, and a peak shaving scenario where the heat pump was requested to convert some excess electricity into heat. We've also compared dynamic versus quasi-static district heating network simulation, performing also a sensitivity analysis and the co-simulation time step. So this is basically the simulation time step at which the orchestrator, MOSAIK, is interacting with the different simulators to exchange data among themselves. And this has been done for a 143 kilowatt electrical heat pump. So some results and discussion here. So here is a first comparison for the peak shaving scenario and their dynamic simulation of the district heating network. So we can see that on top here we have the power limits from the thermal integration that vary for the heat pump. So not only they vary, but they actually vary from a factor 2. And we can see that the most restrictive constraint navigates between the rated power for the heat pump, the constraint from the evaporator, and the condenser. And that basically on the bottom is reflected because the power requested to be converted into heat is not always met by the heat pump. And that is because the thermal constraints basically propagate to the electrical domain. And that comes from the fact that the mass flow situation in the district heating network is actually affecting whether or not the heat pump can exploit its full rated capacity. And this effect is actually most significant at noon, where we actually request the heat pump to convert most of its power into heat. Second comparison here is we've shown that the maximum electrical consumption of the heat pump varies over time, and to isolate that effect, we actually checked on a step activation of the heat pump and their constant operation in the district heating network. We can see that here at a step activation at noon, there is a spike in the thermal constraints that gradually decrease in steps after 20 minutes. So these are the solid lines. This is under a dynamic simulation, and under a quasi-static simulation, we see that there is actually no gradual decrease. So we don't capture these dynamics occurring after the step change. And to understand these gradual effects, we actually have to look at what's happening at the heat pump level. And we can see that after the step activation, there is also a transient in the heat that is absorbed at the evaporator and released at the condenser, as well as in the COP, that is decreasing. And that is because as the heat pump starts operating, the heat pump is working over a larger delta T because the return water is being cooled down and the forward water is being heated up. But we can also see that there is an effect of on the mass flow that the heat pump is undergoing in the district heating. So that means that the heat pump activation actually affects the mass flow in the district heating network. And to understand that, we have to look at what is happening into the district heating network. So here is an overview of the district heating network consumers that are hydraulically located downstream the heat pump. And we can see that after the step activations, the consumers that are closest to the heat pump, they actually see hot water coming in first. And as the hot water is reaching them, they start to close their valve to actually meet the desired constant return temperature that they are asked to deliver back into the system. And actually these steps effects are each of the consumer that is seeing the increased temperature resulting from the step activation of the heat pump. So they close their valve one after the other, which explains the different steps that are propagated upstream at the heat pump level. And again, under a quasi-static simulation, these steps are actually not properly perceived by the simulation. So this is actually important because a quasi-static simulation doesn't capture the delays and transients that are induced by the travel time of water, and therefore the dynamics and heat pump flexibility cannot properly evaluate it. Finally, we looked into some computational accuracy and trade-off. So here, the first trade-off is between the dynamic and quasi-static simulation. So we can see a quasi-static simulation always introduces some error. So both for like critical node supply temperature in the district heating network, and also an electrical dynamic, which is the maximum power limit for the heat pump. On the other hand, a dynamic simulation actually is very accurate up to 120 seconds, so 2 minutes time steps. And after that, the error increases largely to reach like over 15% for a simulation time step of 1.5 hours, for instance. Then the idea was to check whether there was an actual trade-off for the co-simulation time step within the dynamic simulation. And here is a sensitivity analysis for different co-simulation time steps: 1 hour, 15 minutes, 10 minutes, 5 minutes, and 10 seconds, which we consider to be the most accurate and the absolute truth. And you can see here there seems to be a Pareto front at delta t for 5 minutes, where the error and computation time stays reasonably low. So in conclusion, we actually managed to develop a generic toolchain for integrated energy system simulation using co-simulation. We showed that thermal constraints propagate into the electrical domain, and that heat pump cannot always convert all excess electricity into heat. And that is because you need a dynamic simulation of the district heating network to actually capture the true flexibility potential of these units. We also shown that a simulation time step of 5 minutes for the district heating network is could be sufficient, but should be tuned according to the accuracy and needs of the simulation. Some future work, systems with much larger scale. So this system is fairly small, more power to heat units to look into aggregation, and also some optimal operational strategies and more complex controls such as MPC or coordinated control between both systems, and a complete dynamic modeling of the integrated energy system. What is needed is still some standardized test cases for integrated energy systems, such as the IEEE test cases, and open sources district heating network models and the district heating standards. Yep, that's it for me. Thank you for your attention.
Thank you, Thibaut. Very, very interesting work. And we also got a question from Mats. He's asking about, given the complexity of the modeling, the interaction of different modeling tools by this platform, how have you validated your platform, the modeling you developed?
So you mean like
what data did you use, and how did you validate this?
So from a purely simulation perspective, or the actual
well, simulation, I'm sure simulation, or what you put in, you get out. But do you know whether your platform is actually reflecting the real world performance of this kind of systems?
So the data used in all simulations are existing real data from the area in NORDHAVN that I shown. So both the electrical consumption and heat load profiles and everything have been validated beforehand. So the network has actually, the district heating networks is properly reflecting the dynamics of the real system that we've used. Yes.
And so and have you validated your outputs with actual measurements?
Yes, we did.
Good. All right. Okay. I think there was a question. Okay, great. Thank you. We have another, just very quick. Is the software open source?
So MOSAIK and all the tools used are open source, except for the district heating network model, which has been coded in Daimola, and that's so the programming language is open source. It's Modelica, but the platform Daimola is commercial.
Okay.
So that's the only block that is not free, but could be substituted easily, and that's why co-simulation is interesting for that.
That's good. Okay. Thanks again for a very nice presentation. Again, not sure we can clap, but that's on my side.
Thank you.
Thank you. And let's move on with next presentation. Next presentation is by Ignacio Sada. The title is An Adversarial Model for Attack Vector Vulnerability Analysis on Power and Gas Derivatives.